Thank you everybody for being here. I'm super excited to be here. Thank you to the organizers for inviting me and the rest of the speakers here. It's a great honor, and it's my second time in Barcelona. I'm very excited. I've gotten to do some sightseeing. It's a beautiful city, and we've eaten nothing but delicious food so far. I hope to return the favor and talk about something interesting here for you guys this morning. It is a little bit early. I hope everyone had their coffee because we're going to start out with a bit of an abstract topic, but I promise you, how many people write code every day? Okay, that is fantastic, because about half of these slides have code on them. I think that's my one saving thing, is that while I'm talking about something very abstract, I'm going to show you code so you believe everything as I go along. Okay, so here's the idea in a nutshell. That's a good idea. I probably need that. The big idea is that every time you write code, it acts as a machine. We understand that, right? Like, we can put the machine in the world and it does useful things for us. If we write code in a particular way, it can actually allow us to think more clearly and work on bigger, harder problems. So how do we do that? That's the question, and that's what we're going to talk about here. This is sort of a complicated thing for me because I have to change the slides on this because I can't see behind me. So bear with me. I may be playing with this a little bit. In the last 20 years, the world has changed while we've been busy writing code. And it's a bit like that boiling frog. You may not have noticed it. About 20 years ago, you probably ran code on computers that you owned. You probably had individual people going and putting the software onto the computers in order to put them in production. And you released software very slowly compared to what we do now. In fact, if you think about Microsoft Windows, they're still sort of on a yearly cadence or something like that for delivering new software. And finally, even if you didn't have someone who was called an architect, you centralized the decision making for how the software was designed. All of those things have changed in the last 20 years. We generally don't run code on our own computers. We generally use software to push that software into production in an automated way. We have a very quick cadence by which we make software go into production. And perhaps most importantly, there is no central person in an ivory tower making the decisions. So we're all making those design decisions. I'm very excited about this graphic because I made it myself, a little GitHub repository with a crown on it. I think it looks not bad for somebody who writes software for a living. So the second thing that's happened is that the code has become king, okay? And basically, if you didn't check it in, it doesn't count, okay? Now, this is very different than it was 20 years ago. We used to, and we still do, work on analysis, and we do design documents and other kinds of things. But right now, it's either checked in or it doesn't count, right? The major metric that we use for seeing forward progress is code that has either been committed to the repository or pushed to production. The rest of this talk can be thought of as, broadly speaking, talking about design intent. But I wanted to tell you first that the design intent from 20 years ago or more is not the kind of design intent that we need today. 20 years ago, there were a lot of different ways that we were thinking about the problem. We were writing it in analysis documents. We had notations for these things. We would schedule work on design documents. We don't do that today. Instead, we have a tighter, more continuous loop between the software developers and the code that they write. And so I think that there's really a change in the cognitive task that is happening. So while we talked about design intent in the past, that was really, the design intent was the final expression of our thoughts, okay? And you might put that into the code. And I want to compare that with what we do today, which is that there's a tight loop between the software developer and the code. And I'm going to say something that might seem outrageous, but I'll back it up later, is that it allows you to think bigger, more complicated thoughts if you're looking at the code than if you were not looking at the code. And I think it's a big difference. So the rest of this talk is going to have three major parts. Each one of these parts is going to start with a concrete example, usually with code, so you believe me as I go forward. The first one is about theory building. The second one is about distributed and extended cognition, and the final one's on situational awareness, okay? And at the end, I hope to have convinced you that if we do write our code in a certain way, it will allow us to amplify our thoughts. And so the last section then is looking at what we're doing today and comparing that to how well we could do it and looking for places we can do better. Okay? So each of these three sections coming up, theory building first. Let's start with this concrete example. Let's imagine you're at an airport or a train station, and we've all had the situation where they get on the microphone and they make an announcement and the two announcements interfere with each other, right? We've all had that experience. So let's imagine that we have some software that's managing that problem, okay? And we start out with the idea that there's only two speakers. So here's some plausible source code. By the way, none of the source code is meant to be tricky. You're not looking for syntax errors or like subtle problems. That's not that kind of talk, okay? So here's some plausible source code, and it says if you want to get on the announcement, you need to have the start time be when the other one finishes, okay? That would prevent them from overlapping, okay? And this seems to work out okay for two speakers. So what happens, of course, is that someone says, I want to handle 3 speakers, okay? And I look at my old source code and say, that isn't gonna work because the old source code only stops 2 speakers from overlapping. Everybody with me so far? Okay. So we do some very small change to the code, and we actually now handle 3 speakers. And we say, look at the second speaker and the third speaker, and whichever one is farther in the future, use that as the time when the announcement goes on. Okay. Now, the requirements person comes back to us and they say, actually, you didn't understand this. The next thing we do as a software developer is we say, 3, I can do n. So once you could do 3, you might as well do all of them, okay? So what we do is we generalize it to all speakers. But then our requirements person comes to us and they say, actually, you didn't understand the requirement quite right. Not all of the speakers interfere with each other if they're playing at the same time. And it turns out that third speaker is very far away. So you don't need to worry about it interfering with the first 2 speakers. So that code that you wrote that said, look at all the speakers, that's not the right thing to do. Okay, so we have to go back to our code. And we say, actually, what's important is the distance between speakers. Okay? Now, if the 2 speakers are close to each other, they could overlap with each other. But if they're far apart from each other, it doesn't matter. So if there's a building over there with a speaker, don't have to care about that. So here's some plausible source code that says, you know, if they're 20 meters away, then they're not going to interfere with each other, but it's basically the same as the old source code. Make sense so far? Okay, great. But notice that we were still using that language of overlapping speaker announcements. And that's not quite right. It's not a matter of overlapping, it's a matter of interference, because the third speaker can overlap with the first 2 and not cause any problems. So we changed the language a bit in our source code to talk about interference. And then finally, we had that constant in there of 20 meters, which the next person's going to come along and not have any idea why 20 meters is in there. And we at least give them a hint here, and we call this a safe distance. So with all that, hopefully you believe me that we progressed along and we wrote some software that looks plausible. And I'd like to introduce now the idea of theory building. Theory building comes from the mid-20th century. There's a philosopher who was trying to say, what does it mean to understand something? And he talked about the idea of building theories to explain things inside of our heads. So Turing Award winner Peter Nauer wrote a great essay. I highly encourage you to read this thing. And this is how it opened. It said, programming properly should be regarded as an activity by which the programmers form or achieve a certain kind of insight, a theory of the matters at hand. This suggestion is in contrast to what appears to be the more common notion that programming should be regarded as a production of a program and certain other texts. Okay, so he wrote that very stiffly, but here's what he's saying. He's saying that some people think that programming is typing programs into a computer and running them, but really, programming is about coming to an understanding of the problem and a suitable solution, okay? Here's how you might convince yourself that that's true. Imagine on your current program that you're working on that you keep all the same people, but there was a tragedy and you lost all your source code. How long does it take you to recover and rewrite a new program? The answer, generally people say, is much less time than it took the first time around because you've developed all those ideas in your head. You've lost the code, which was very valuable, but at least the ideas are still around. Now, if you flip that around and you say, we've got a bunch of source code, but we don't have the ideas in your head, then we come to the problem that one of the other speakers, Michael Feathers, likes to talk about a lot, which is how do we recover those ideas so that we can make forward progress with our source code? So that's what theory building is all about. So let's return to the example that we were working with, and let me show you the kinds of evolution of the theory. We started out with a theory that included just 2 speakers and overlapping. We then worked into 3 speakers with overlapping. We generalized that to n speakers. We changed the idea of overlapping into interference and talked about distance being the important part. And then finally, we encoded a heuristic for a safe distance. Now, the reason I'm pointing this stuff out is while we showed that in the program, the important part was the theory that was changing and evolving in our heads, okay? And that's a very valuable thing. Let's go back to the source code. Do you guys remember how the things evolved? We had source code that was working for 2 speakers, and then the requirements person said 3 speakers, and we wrote some code, we misunderstood the requirement, and so forth. But if you think about it, that 3rd speaker was very far away and did not interfere with the first 2. Okay? So let's imagine, let's go backwards in history and pretend that there was no misunderstanding. In which case, you don't even need to change this source code, right? Because the original source code prevents the first 2 speakers from interfering. The 3rd speaker doesn't interfere because it's in another building or something like that. And imagine you'd had all those thoughts in your head. You could continue running the old source code, right? You don't need to change the source code. As a machine, the old source code handles that 3rd speaker requirement. It doesn't handle n speakers, but it handles 3 speakers correctly. You probably worked with a coworker who would leave this code checked in, right? And when you come to him and say, like, why does this possibly work? He says, well, actually, the 2 speakers are like this, but then that 3rd speaker is very different, right? You have to talk to that person to learn why that is. Here's the source code that we wrote together. I'm going to argue that this source code gives every one of us a better chance of recovering the theory that was going on inside the people's heads. It's that theory that evolved step by step as we understood the problem and solution better. So this is the slide we'll see over and over again. That was the first section talking about theory building and what that's all about. On the right-hand side, you see a bit of a diagram. Let me explain what's going on with that. In the thought bubble for the person, the left-hand side is meant to be the long-term thoughts that are in this person's head. It's like the things that you already know before you start looking at source code. On the right-hand side of the thought bubble are the thoughts that are going through your head right this minute, like short-term memory kind of things that you're working on right now. And down at the computer, the person is looking at source code. And so with this example with theory building, I'm suggesting to you that if you are looking at the theory and you're thinking about the theory, that things work out better, okay? And of course, we have to check it into the source code repository, and the code is king, okay? So in the next section, I'm gonna support that bold assertion that you're gonna be able to think harder thoughts if your source code lines up with your thoughts. So that's extended and distributed cognition. How many people have heard of these terms before? Okay, yeah, these come from the psychology literature, so I'm not just making this stuff up. So here's an example of extended cognition, and I'm going to go through this very quickly. If you're interested, there's other talks on the internet. Most of you, if I give you 2 single-digit numbers, can add those almost without thinking. What about 2-digit numbers? Yes, you can do that in your head. Maybe about 3-digit numbers, that starts to get a little bit harder, and at some point you stop being able to do the math problem in your head, okay? If I talk about programming, the same thing is true. How big of a program can you write in your head? Only a couple lines at a time. But with both the math problem and with the programming problem, if I let you have your thoughts spill out onto a piece of paper, suddenly you're able to do much, much bigger tasks. So here's an example. So extended cognition is this idea that you can have bigger, harder thoughts. You can actually work on harder problems if you allow your thoughts to spill out onto paper as an external representation. But there's a trick. Not every external representation works equally well. So let's go back to that math problem. I think all of you will have a very easy time doing this math problem, right? You just go column by column and add up all these numbers. If I just make a very small change to it, it's not as easy. It's still better than doing it in your head, but it's not as easy. The point I'm making here is that it's critical what form the external representation takes. And if the way that you're thinking about it in your head is in terms of adding up columns, and the thing that you're looking at does not make it easy to align the columns, then you don't get that cognitive expansion. So I think it's a very small jump to say, if I'm trying to have thoughts about computer programs, but I'm looking at a program that doesn't reveal those thoughts, you're having to do extra work and you're going to be slowed down. You're not going to do it as effectively. So let's take a look at another very simple program. Again, the source code isn't all that important. I just want you to take a look at it and you can sort of see that there's a stoplight and that it's going to be green in one direction for 30 seconds and then it's going to be green in the other direction for 15 seconds, okay? I think we'd all agree that this is some plausible source code that could run a traffic light, okay? It works fine as a machine. But as soon as you start thinking about having to evolve and maintain this program, you run into a pretty big obstacle. Because you can sort of see that there must be a reason why one is going 30 seconds and one's going 15 seconds, but you have no access to the thoughts that led up to that conclusion. You see what I mean? Okay? So as far as this source code goes, it's not as good as some other source code that gave you the ideas that were in the person's head when they came up with 15 and 30. So that was extended cognition. That's one person's mind and a problem. But almost none of you, I bet, work on teams that only have you as a programmer. In fact, we almost always work in large teams because the problems are large. So here's an example of a bunch of guys on the bridge of a ship. And the reason there are a bunch of people on the bridge of a ship is because the problem, again, is too big for one person to do. Otherwise, they would just have one person. Now, on the left side of the screen there, you can see that there's a display. And so the same thing that was going on with a single person and extended cognition is going on here in the group. There's one person in charge of navigation, perhaps, and he's got marks and squiggles on that screen. So the internal-external loop applies in a group setting, but there's extra constraints. Have you ever been in a situation where the source code works for your coworker, they can maintain it and it makes sense to them, but you go into that source code and it's just not working for you, right? So you have this extra problem that while the external representation, you have to have that loop going for an individual, with a team, you need everybody to be able to share those theories, okay? So it's not enough for it to work with just that one person. It has to work with the team. So I would say that when you've got this group of people that's trying to work on a cognitively demanding task, you've got 3 hurdles. You have to have good theories. And what I mean by that is, I don't know anything about steering a ship. If I came up with a theory about how to steer a ship, it's not as good as whatever they're doing, okay? And probably the same unless you're a sailor. The second thing is you need to have a good external representation, okay? So, for example, those marks on that computer monitor must be a good way of reasoning about where's my ship and where are the other things. And then finally, that you need to make sure that everyone on the ship, everyone in this team, shares that theory. Otherwise, you're not going to do a good job. Okay, back to this diagram you're going to see several times. The first part we talked about was theory building, which is the idea that there are these theories, they're a real thing, and we may or may not see them in the source code. The second part of the talk here was extended and distributed cognition. And I made that bold statement that you may not be able to think quite as clearly if the source code is in one format or another. I hope to have convinced you that that may be true, right? Like you may actually need to be paying attention to that. And so in the diagram on the right, the arrow being highlighted is trying to say that you want to align the things that you're thinking about right now with the things that you're looking at right now because you're going to get better performance. The last section we're going to talk about is situational awareness. Situational awareness is again, comes from the psychology literature, is this idea that as people, we're going through a loop of looking at the world, trying to figure out what's going on, and then making some actions. And that the tighter we can make that loop, the more effective we can be, okay? So it's difficult for me, standing here on stage, to drop you into a very large code base and make you feel confused, okay? We've all felt that before, right? You're like, what is going on with this code? But what I can do is introduce American football to you. Does anyone consider themselves an expert in American football? Okay, great, perfect. You're going to be completely confused, but not completely confused, because you see this diagram here? This diagram here is for a nickel-back defense. Does anyone know what a nickel-back defense is? Perfect, you're going to be confused. So what I'm going to show you on the next slide is not something that your eyes are going to have any trouble seeing. It's simply that you're going to have a hard time perceiving what's going on. A nickel-back defense is when the defense has 5 defensive players in this arrangement. Okay, so you ready? I'm going to let it loop a couple times. Okay, so who wants to tell me if that's a nickel-back defense or not? I showed you the diagram. I mean, I'll show you the diagram again if you think it's going to help. Okay, my point being is that when you are looking at something, it is not a matter of are your eyes perceptive. It's a matter of are you ready to perceive what's going on. And I threw you into a situation where you're not ready to perceive those things. So the formalization of a situational awareness loop goes something like this. You need to literally perceive what's going on in the world. You need to put that into some sort of mental context that makes sense. Then you need to forecast into the future. You then make a decision to act on something, and you act. And you repeat that cycle over and over again. In fact, you're doing it right now, is the argument. Like, we're always doing this in the world. You know, should I go to this great conference that's about to happen? Yes, I will buy a ticket and I will attend. Okay, you're going through this cycle. So when you are trying to figure out what's going on in that example, your first problem was that of perception. What the heck is a cornerback? And if you can't see a cornerback, then all the rest of the stuff is not going to happen. It's not going to click. Okay, you won't be able to figure anything out. Oh, by the way, I have a simple question. On which side of the screen was the defense? Okay, but the point is, like, even very simple things, you have to be like, ah, okay. So the source code that we saw at the very beginning here, this thing works as a machine, but it fails as a theory. This source code that we saw before again, this actually both works as a theory and as a machine. And my argument is by making these things evident, these thoughts evident, you're helping your other programmers and yourself perceive what is actually going on. Because you can't assume that they're going to drop into this code and understand all the context that you have for it. So I like to think about this in terms of 2 people standing on the side of a sports event. And if you would like, you can change this over to an example where you're kicking a ball with your feet rather than throwing it with your hands, and that's perfectly fine. So here we have a coach and what we call in the United States a rookie, which is a novice player. And the thing I'd like to point out here is that the novice player is actually the one who's doing the work. He's out there playing the game. He's stronger, he's younger, I bet his eyesight is better. There's a lot of things that he's got as an advantage. But the question is, who has better awareness of what's going on inside the game? I think you're going to agree that it's probably the coach. And I'm going to suggest that the reason the coach is ready is because in the back of his head, he's already ready to know what a cornerback position is or what a particular defensive arrangement looks like. So when his eyes get that stimulus, boom, he's ready. He understands it, and he's got that little tight loop of like perceiving what's going on, putting that into context, then knowing what's going to happen next, making decisions and actions, okay? And when we don't have that awareness, we run the loop very slowly. And I hope you will have, you can reflect on when you get dropped to a big new code base, that you don't understand what's going on. And I think this is the thing that gets broken. So then I need to tell you a true story, okay? And I hope you guys have studied your design patterns. So a friend of mine writes some code as he's just arrived at a new company, and in the commit message sending out for review, he says, this code uses the strategy pattern ... to do some stuff. So the code reviewer writes back and he goes, why are you talking about strategy? And my friend says, not strategy, the strategy pattern. And the other guy goes, what's the strategy pattern? Which hopefully is a nice joke, but I see that it's not landing, which means that design patterns are not such a big thing anymore. My point being with this example is that my friend had very clearly dropped breadcrumbs. He'd left clues for the next person that says, I am using the strategy pattern. If you don't already have the strategy pattern tucked away in the back of your head, that doesn't help anyone, okay? So, in terms of making code a partner in your thoughts, we've talked about three things. First is that theories are a real big deal, and your code may or may not express those theories. When the code does express your theories, you can get a very efficient loop going on between what you're thinking about and what you're looking at. And my argument is you're actually going to be more effective. You're going to be able to think harder thoughts and work on harder problems. And that last point about situational awareness is that in order to run the situational awareness loop very, very fast, very tight, very accurately, you need to do some long-term learning and get things stuck in the back of your brain so that you're ready to perceive them when they happen. So that's the sort of cognitive model that I want to introduce. I'm going to just do quickly some ideas about what we're doing now and what we could do better. So one thing when I look at processes right now, they're incredibly feature-driven. It's hard to argue that they should not be focusing on features, but let me suggest that there's a problem when you only focus on features. If the pointy-haired boss on the left keeps saying feature, 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 you've got a team over on the right that's adding features to the source code, and if they do not have a chance to evolve that source code to reveal their current theories, then you're going to get a big ball of trouble, right? Because they're going to keep pushing that snowball, and it's going to get harder and harder. When we look at other industries, and if you think about cars, cars are getting better every time they release a new car, okay? And that doesn't feel like our software industry. It feels like every new website that gets thrown up could be making problems that were figured out 20 years ago. We need to be thinking about how to keep our theories improving, and that is the way that we can get to the future. We can emulate that in every other engineering discipline that they push their theories ahead. The original, I encourage you guys, if you haven't already, to take a look at the original paper on technical debt by Ward Cunningham. It's only like 1 page long. It's super, super short. And secondly, he put out a video, which again is like 5 minutes long, about technical debt and his understanding of it. In both of these, I see a very strong flavor of him saying, I needed to develop these thoughts in my head. As those thoughts evolved and I looked at my old source code, when those things were mismatched, I had low performance. And so he was going to his boss and saying, my ideas and understanding of the finance industry have evolved. I need to change the source code. And the boss is looking at him going, but the code works as a machine. We don't need to change it. And his argument for introducing the term technical debt and arguing for refactoring was because the theories had evolved and you needed the source code to catch up so that he could have high performance. It's possible that some of you are running a software process that looks something like this. You get a new requirement, you write a test case because you're doing test-driven development, right? So for the new requirement, you write the test case and it fails. You edit the code enough to make the test pass, and then you do enough refactoring, okay, to remove any duplication, which is not a very high bar, right? You need to go higher. So let me compare that with another process that has theories inside of it. The same thing, you get the requirement, but when you get the requirement, you're comparing it against the theories that you currently have, okay? Do I need to change the architecture in order to accommodate this theory? Do I need to change the domain model in order to accommodate this theory? And honestly, most of the time the answer is no, because you've already predicted enough things, you've done a good job of those things. But if you do need to change them, you do. And then you go ahead and write the code and get things lined up. There's 3 different time horizons you can think about that, like on a weekly cadence, your team is probably doing exactly what they do today, which is they're building theories and they're deploying code and so forth. But at the medium term, there's the evolution of the theories, right? That they're actually changing and that you need to be going back into the source code and doing aggressive refactoring to make sure those things line up. And in the longest term, you're getting to the point where you're saying, I want to grow my developers. What do I need to get stuck in the back of their head so that they're ready to perceive the next set of theories? Okay, so that's the talk. I started out with this idea that the world has changed, that the code repository is king, that we need to check in code or it doesn't count. So my suggestion is that architecture is just as important as it ever was. We should be finding ways to express our theories about architecture into the code, because that's what we're going to be looking at all day long. The cognitive task has actually shifted over the last 20 years. We used to have longer development cycles. We were thinking and putting our thoughts into documents. We would track the development and delivery of documents, which we do not do anymore. We're instead just tracking code. We used to think of the code as a place where we're building a machine and it might have some of our design intent. And my argument is we're operating in very quick cycles. We're checking in code every day and maybe even deploying it every day. The code has become a partner in thought, or at least it has an opportunity to do that. And so I'd encourage you guys to look for places where you can do that in your code tomorrow. Thanks very much. Appreciate it. Yeah, if we have time. Yeah. It was, according to the internet. I have to admit that on that, I have such a hard time tracking who's doing what. I did show it to some people that did seem to know football, and after the second playing of it, they said, yes, it is a nickelback defense. But I still find that a very compelling example, because it is, things are fluid, right? And so there are other clues, actually, and maybe it's the same thing in the other football. But the numbers on people's jerseys indicate what things they're allowed to do and what positions they're allowed to do. So I think my friend was also looking at the numbers on the jerseys, which is something I don't have access to. Yeah.
You mentioned an article about technical debt, or a talk, or a paper. Can
Yes.
you please mention the author as well?
Yes, absolutely. So the term technical debt was first invented by a guy named Ward Cunningham. If you've ever heard of, has anyone ever heard of wikis? He also invented wikis, by the way. So like just some very minor accomplishments, okay? The original wiki is at c2.com, which was Cunningham and Cunningham.com. So a very early website that you can get 2 digits in the name. The name of that paper is something about the YCash portfolio management system. I think it's from 1992 in Uppsala. And it was an experience report, so it was just 1 page, yeah. The second one is if you look for the terms Ward explains the technical debt metaphor. Then you'll find, again, it's about a 1-page description there.
Another question? Hi, thanks. So I have a question about, maybe it's a double question, about how do you deal with the theories that cannot be expressed in code?
Yes. I'm so glad you asked that question. It is absolutely the case that it is difficult to express some ideas in source code. In fact, I'm going to plug my book. No, actually, usually Simon Brown is the one who's excellent at plugging my book, because he likes to talk about the model code gap, okay, which is a term that I was using in the book. The examples of things that are easy to express are things that you can enumerate. If you think about source code, if you say there's an A and a B and a C, you can write source code that says there's an A, there's a B, and there's a C. Maybe you declare classes called A, B, and C, or declare functions called A, B, and C. If you have to enumerate it, it's very easy. Okay. Now, if you do that upside down A in the logic stuff, and you say it's always the case that such and such is true, or it's never the case that such and such is true, that tends to be very difficult to express in software, right? So the example I like to use is, imagine you had a 3-tier system with a user interface and logic and then persistence, okay? And you want to say, under no cases can you talk from the user interface directly to the database. You always have to go through your server in the middle, okay? Pretty difficult to express in code. If you're highly motivated, you'll probably find a way. And so, for example, one way I know people do that is they express build dependency rules. And so you basically say, fail the compile step if you try to pull in the Postgres library or something like that. Okay, so there are ways of doing it, and of course, remember, there's always comments. And I think one of the most underappreciated things that the source code repositories have now that we didn't have 20 years ago is you can put a README file in any directory. Okay, so for that little bit of stuff that you want to say, hey guys, there's stuff that I couldn't explain in the source code, there's always the README file that's probably in the same directory. Let me say one more thing about that, is that sometimes focusing on the theoretical limits of what can't be expressed paralyzes you from doing the 90% that you can that's very easy to do. Okay, so for example, in analyzing programs, we understand that the halting problem exists, right? It's impossible to tell if this program is ever going to terminate. How many people have deliberately written programs that never terminate? Like, you know, we really try to avoid that, okay? And so for a long time, people didn't look at static analysis of source code very seriously because they were scared away by the halting problem. But what it turns out is that the code that we write tends to be far more analyzable than you would expect, which is why every year it seems like inside your IDE they have another analysis that says, by the way, did you notice that that's going to be null? Or by the way, did you notice that you're using a bad locking pattern for concurrency? It's really impressive what they're able to do there. So focus on the positives of what you can express. Yeah.
Hello, thank you for the talk. So my question is, are you for or against like centralized wikis with all the documentation, diagrams, etc.? That's, I think, very typical also in software.
That's a very broad question. I think you need to have it in context to answer. It sort of sounds like a discussion you might be having at work. Let me suggest this. At some point, let's imagine, let me make an exaggerated example. Let's say that we had a reasonably small program, say 10,000 lines. And over here on my wiki, I had 10,000 pages of descriptions of the program, right? Even if everything was answered over in the wiki, people may never read it, okay? Because of just the time it would take to read compared to the time it would take to run the program and come to an understanding, okay? So you always have to strike that balance of how can I, well, in an ideal world, the source code would carry a lot of the explanation. Okay, so if you get to the point where you feel like you can make safe changes to the source code because you understand it well enough, then you may not need to look at the documentation, okay? But the documentation can tell you things the source code will not. So in an example, let's say there were 3 ways you thought of to do something. The source code is probably not going to tell you about the second and third way that you chose not to do. And there might be some really important things. Here's a simple example. 10 plus years ago, I built a Hadoop system, okay? And we had to do some MapReduce processing. And when I looked at this, I said, you know, we don't want to be writing raw MapReduce things. There was this higher level language called Pig. And so I said, let's try writing the program in Pig, even though it's a very weird language, but it let you write higher level operators like SQL joins and things. Some of the people were not part of that analysis, did not know that we looked at these 2 things and chosen Pig. And so for a long time, they kept agitating and saying, I want to write raw MapReduce jobs. And so at some point, someone said, go ahead. You know, if you can write them to run faster than this optimized language, then that's great. So they spent some amount of time, and then they said, oh, actually, it's very difficult to beat the performance of the tuned language that does the joins for you. Anyway, my point is that, yeah, this can really happen. It can be difficult to communicate design decisions, and you may want to do that outside of the code. Okay, thank you guys very much.